Hi, I'm Stephanie, and this is The Cool Part Show, the show all about interesting 3D printed parts. You may have heard about the possibilities of nuclear fusion for power generation. This is the same type of reaction that powers the sun and other stars, and it could be used to generate power down here on Earth. It's not science fiction. We are making progress towards being able to apply nuclear fusion in the energy sector. But doing that will mean having the right safeguards in place, and that could call for 3D printing. We're looking at 3D printed tungsten divertor tiles for nuclear fusion reactors on this episode of The Cool Part Show. Welcome to The Cool Part Show, and thanks for joining me. Today on the show, we are looking at 3D printed tungsten divertor tiles for use in nuclear fusion. These are essentially part of the safety mechanism that would keep the fusion safe and stable. So the samples that we have here today were provided by Oak Ridge National Laboratory, which is sponsored by the U.S. Department of Energy. These hexagon pieces are the actual tiles, and then the rest of these parts are showing what it would look like assembled together as a section of a wall inside of a nuclear fusion reactor. But I'm getting a little bit ahead of myself. Before we get any farther, let's take a pause and talk about what nuclear fusion actually is. So I want to introduce our first expert for this episode. This is Troy Carter. He is the director of the Fusion Energy Division at Oak Ridge National Laboratory.
So what is the difference between fission and fusion? They both tap the energy of the nucleus. They both make use of what we call nuclear binding energy. You can think about that. So the nuclear particles, protons and neutrons, they like to bind together because of the strong nuclear force. And you can think about that force as kind of a rubber band that snaps them together. And in that snapping, you release energy. So it turns out for fission, you take very heavy stuff, uranium, and by breaking it into two pieces, it snaps together more strongly than it was before. So you actually release energy in that process. And for fusion, it's going the other way. You take very light elements and bind them together and release that energy. You can fuse almost anything, it turns out, but if you the easiest fusion fuel to use are isotopes of hydrogen. So the highest probability reactions. If you look in the core of our star, the sun, it's just fusing protons together. So four protons get fused together into a helium. But that's a very, very difficult reaction to do in the laboratory. But luckily, there's an easier one that uses heavy hydrogen, so deuterium. That's hydrogen with an extra neutron. That's abundant in water. So heavy water contains deuterium. And tritium, which is even heavier hydrogen, so an extra neutron. Turns out that has to be manufactured because that's is not found in nature. It is radioactive. It decays away once you make it. So that one of the tasks for fusion scientists and engineers is to find techniques to breed the tritium you need to make the fusion reaction work.
So Troy mentioned deuterium and tritium. These are hydrogen isotopes that have 1 and 2 neutrons respectively. And when a deuterium atom and a tritium atom fuse together, they make one helium atom and also an energetic neutron, which would be the source of energy for power generation. Here's Troy again.
So a diverter is utilized in magnetic confinement devices. So these are devices that hold the plasma together using strong magnetic fields. In those devices, you have to have a mechanism to exhaust the waste, the ash from the reaction. So helium, you want to get it out of there. You also need to pull out some of the heat through a process where you get transport of the particles and energy that are confined in the middle. They eventually walk their way out. You develop a magnetic geometry that takes some of the outside region of the plasma and diverts it down to this diverter, okay, where you actually can accept this very strong particle and heat flux. So you need to have this very robust structure that's going to be able to survive a lot of heat flux, a lot of plasma particle flux, and neutrons irradiating it. So it's a challenge, but this is important for magnetic confinement fusion devices to have a diverter.
So the diverter sits at the bottom of the magnetic confinement device and functions as sort of a funnel to direct those offshoot particles away from the reaction and keeping everything safe and stable. And it would be lined with tiles like this to help direct those particles and prevent any damage to the system. So the prototype tiles that we have here are 3D printed, and a major reason to use 3D printing to make these objects is for the material properties. Anything that's going to be inside of that reactor needs to have a very high melting point, and the material used here, tungsten, has an extremely high one. So I want to introduce our second expert for this episode who can talk more about 3D printing and the specific material involved here. This is Mike Kirka. He is a senior research staff member at the Oak Ridge National Laboratory, specifically the Manufacturing Demonstration Facility, or MDF.
There are other aspects to why tungsten is important as a material is byproduct of the fusion process is tritium, and tungsten does not retain the tritium within its crystallographic structure. But also it's of the materials available, it offers the lowest nuclear activation of what it currently exists.
But in order to use tungsten in this application, we need ways of manufacturing parts with fairly complex geometries. And tungsten is pretty difficult to manufacture with conventionally. It can be machined, but it is challenging. It can also be formed with like a press and sinter process, but the geometric possibilities are limited. So to solve for some of these problems in manufacturing, Mike and his team have been looking at 3D printing parameters for how to additively manufacture parts out of tungsten. There are a couple of different processes that can be used to 3D print with tungsten, including laser powder bed fusion, but here we're talking about electron beam melting, or EBM. This is another powder-based process that uses an electron gun as the energy source to fuse and melt the powder together. We actually have a whole other 101 video about EBM. If you want to check that out, we'll drop a link to that in the show notes. But it turns out that EBM is actually a pretty good process for working with a material like tungsten.
Specifically for tungsten, why we chose this was for three factors. One, the vacuum environment, limited interstitial, i.e. oxygen contamination pickup, which is very detrimental to tungsten and refractory alloys. Also, there's the ability to preheat the powder bed to high temperatures, which you cannot achieve within the laser powder beds today. So we're looking at temperatures in excess of 1400 Celsius in the melt area, which aids in us maintaining thermal gradients, especially when we're trying to stay above the ductile to brittle transition of tungsten. And lastly, the other main point is the ability to manipulate the electron beam in a manner that to your eye, it looks like there can be tens of 20s of melt pools simultaneously or beams within the chamber when it's still only one electron beam. And this helps us control the stresses that develop while printing parts. And it's these three factors together that make electron beam melting a unique technology that you can't get them all in other technologies.
So electron beam melting with tungsten potentially leads to better material properties along with these more complex geometries. So these tiles have these fairly deep slots, there's this deep pocket in the back, and these are features that could be machined, but you have to take into account the wear and tear on the machine tool, the time it would take, the consumables, the cutting tools, and other things that would get worn out in that process. And so additive manufacturing offers a simpler and more direct route to geometries like this. And design control is going to be really important for nuclear fusion applications.
You want to make sure that you have no what we call leading edges. Basically, this heat flux, you want it to come in and hit this flat surface without hitting it from the side or having a leading edge where you can have enhancement and erosion. So you want to design it in that way and have the structures that you're building be able to form that kind of pattern or surface to accept the heat flux that's coming down.
So to be clear, none of the examples that we have on the table today are final designs. They're not going into a nuclear reactor next week or anything, but they are indicators of where additive manufacturing could potentially help nuclear fusion step forward. If we have the capability to manufacture tungsten components in exactly the right size, shape, geometry that we need, that's another step towards being able to apply nuclear fusion for power generation. So another important note here is that these divertor tiles are not meant to be permanent fixtures inside the system. They're going to be subject to those elevated temperatures, they're going to be impinged upon by neutrons over time, and so there will need to be a way to swap these tiles out as they wear in the course of maintenance on the reactor.
One idea how to make them is to have kind of repetitive units, tiles that you can manufacture and assemble together. So in terms of how these tiles or how the diverter will behave with time, this is actually ongoing research. What we expect to happen, of course, is there's going to be erosion of the material because of this heat flux and particle flux, you're going to have sputtering, you're going to have material migrating around, you're going to have it exposed to neutron damage that may enhance this erosion. So you expect to have to replace it, but there's all kinds of processes where you can imagine damage. And the hope is that you can do things like in situ repair. We have a project here looking at robotic repair of tungsten surfaces. We might be able to do in vacuum or in the vessel without major intervention. But you need to come up with a strategy to replace these. We kind of anticipate that the lifetime, we're hoping we get to a lifetime of a couple of years of a diverter, or at least, most of the diverter. But you have to have a strategy for getting in and replacing it.
So there's more work to be done, and these diverter tiles are only one part of the equation, but they could be one of the factors that helps make the same reaction that powers the sun operational here on Earth. So to recap, these are diverter tiles designed for a nuclear fusion reactor. Their role would be to redirect the particles and heat flux coming off of the reaction to make sure that everything stays stable and safe. These were 3D printed out of tungsten using electron beam melting. Tungsten is a material with a very high melting temperature, making it very well suited to applications like this, but it has been difficult to process with conventional methods. Electron beam melting offers a simpler, faster way to get to complex geometries like this, which could help to enable nuclear fusion. This episode is brought to you by Manufacturing Connected, the new home for the Cool Parts Show. Manufacturing Connected is a platform from our publisher, Gardner Business Media, where we share actionable insights for manufacturing business leaders, regardless of the processes you use or the industries that you serve. We're covering everything from automation and AI to tariffs and workforce management. Go to mfgconnected.com to sign up for our weekly newsletter. In every Tuesday issue, you'll find quick reads with clear takeaways, access to in-depth interviews, and useful links about the issues that matter to your business. Get connected today at mfgconnected.com.